Welcome to This Explainer. Today, we're going to build what I like to call a data refinery. In the world of artificial intelligence, raw data is exactly like crude oil. It's messy, it's totally unstructured, and honestly, in its raw, unfiltered form, it's absolutely useless for powering the next generation of AI models. But today, we're going to learn how to tap into a massive well of raw AI data, specifically these really complex agent interactions. And we're going to build an architecture to refine all that into high-octane fine-tuning fuel. To really understand why we even need a refinery in the first place, we have to anchor ourselves to the sheer scale of the challenge here. We're looking at a massive 1.7 million agentic interaction traces contained within the open-source AgentTrove dataset. Just think about that number for a second. 1.7 million individual traces of AI agents thinking, using tools, and making complex decisions. Trying to open a file that massive the traditional way, yeah, that would literally turn your laptop into a very expensive space heater. It's an incredible treasure trove for sure, but making sense of it requires a highly strategic approach.
Okay, let's dive into the architectural blueprint for our refinery. We're breaking this down into 5 fluid stages. First, taming the massive agent dataset. Then, normalizing the conversational chaos. Extracting hidden shell commands. Visualizing agent behavior patterns. And finally, building the final SFT dataset. Let's get into it.
Stage 1, taming the massive dataset through streaming. When you're dealing with 1.7 million complex interactions, your very first hurdle is simply figuring out how to handle the sheer physical volume of it all without crashing your computer. So we have a classic showdown here. On one side, we have the villain of our story, downloading giant datasets locally. This approach is painfully slow. It eats up absolutely all your RAM, and it's going to exhaust your hard drive storage in no time. On the other side, we have our weapon of choice, a streaming pipeline using Python's Datasets library. Streaming is fast, it's incredibly lightweight, and it processes data dynamically on the fly. You literally only load what you need exactly when you need it. By utilizing this streaming capability, we can actually target the OpenThoughts/AgentTrove repository directly on the Hugging Face hub. We open the dataset in streaming mode and just start pulling in rows dynamically. We don't download a single byte of the full dataset locally to the hard drive. This architecture is what makes processing 1.7 million traces entirely possible and perfectly scalable. In fact, it's so efficient that you can run this entire data refinery pipeline straight from a basic free Colab notebook. Pretty amazing, right? Moving right along to stage 2, normalizing the conversational chaos. Now that we can efficiently stream the data, we actually have to read it. And if you've ever worked with raw AI conversations, you know that different datasets use wildly different schemas. It's a total mess. So we need normalization. As you can see, normalization is just the process of taking those varied, unpredictable dataset schemas and standardizing them into a single, consistent role content format. Think of it like building a universal translator for your dataset so that everything speaks the exact same structural language. To achieve this translation, we build a defensive Python pipeline. Step 1 automatically detects the trace column. Sometimes it's called conversations, sometimes it's messages, so our code just hunts it down gracefully. Step 2 extracts the exact role from that specific turn. And Step 3 parses and standardizes the actual content. Because raw AI output is notorious for being unpredictable, we have to build this defensively. We handle empty values or entirely missing keys so that a single bad row doesn't crash the whole pipeline halfway through a massive job. So the crucial point is that by the end of this normalization step, our rendering function beautifully organizes every single turn into one of 4 clear, standardized categories: system, user, assistant, or tool. Just like that. The structural chaos is completely gone, and it's replaced by a perfectly clean, predictable conversational trajectory. Stage 3, extracting hidden shell commands by parsing actions. Having clean conversation turns is great, but to really understand what an AI agent is actually doing, we need to pull out the specific actions they're trying to execute. Just look at how messy a raw assistant output can be. It's often a chaotic JSON block filled with nested dictionaries, arrays, and a labyrinth of fields like commands, keystrokes, or action. It's an absolute jungle in there. To get exactly what we want out of that mess, we build a recursive parsing function. It acts kind of like a smart sieve, gracefully walking through every single level of the JSON object to hunt down these specific action keywords. And the result of that hunt? Our extracted target. By thoroughly cleaning up potential code fences and recursively digging through the loaded JSON, we cleanly isolate the executable shell commands. We're meticulously separating the pure action from all that conversational noise. This granular extraction lets us explicitly track tool usage and measure exactly how often agents issue real executable commands when interacting with their environments.
Stage 4. Visualizing patterns through an analytical snapshot. So, we've done the micro-level extraction. Now it's time to step back and look at the big picture. Because we set up that streaming architecture right at the start, we don't need to load all 1.7 million rows at once to spot macro trends. Nope. We simply stream a process sample of 2,000 rows, calculate lightweight features on the fly, things like turn counts and extracted commands, and push them straight into a pandas data frame. This gives us a highly powerful analytical snapshot without ever bogging down our system memory.
Now, what's really interesting about this is looking at the numeric summaries. By checking out simple column metrics, the number of turns, the number of assistant or tool interactions, total characters, and command counts, we instantly gain a robust statistical understanding of how long and complex these agentic trajectories really are on average. It is a brilliant way to profile the dataset's density at a quick glance. When we visualize this data frame, macro patterns immediately emerge. We can quickly identify exactly where these agentic interactions are originating from within the broader AgentTrove dataset. Whether the AI was solving complex software engineering problems in SweSmith, competing in challenging Codeforces environments, or navigating R2 eGEM, we can effortlessly map out the exact distribution of tasks. And this brilliantly illustrates something else, too. We can clearly trace the influence of the AI's origin by looking at the top teacher models. By tracking which model originally generated the specific trace, we can deeply study how agent behavior patterns, tool usage frequencies, and overall success rates actually vary depending on which large language model was acting as the teacher. It's a really fascinating look into the lineage and behavioral inheritance of artificial intelligence. Finally, Stage 5. Building the final supervised fine-tuning dataset. This is where our refinery produces its final product. We're going to distill all our streamed, normalized, and analyzed data into a highly concentrated, usable drop of clean, fine-tuning fuel. Because obviously, if we want to train future models, we only want them learning from the absolute best. We definitely don't want to train them on failed logic. So we build a strict success filter. We literally tell our pipeline to scan the streamed rows and automatically drop any agent trace that doesn't explicitly meet our success criteria, specifically targeting tags like resolved, success, passed, correct, or a reward score of 1.0 or higher. The final output of this entire pipeline is a file named agentrove _clean SFT.jsonl. But importantly, we write it out in the widely recognized ShareGPT format. This is absolutely crucial because it means this clean, streamed subset of purely successful traces is now perfectly formatted, plug and play, and ready to feed directly into popular supervised fine-tuning workflows like Axolotl or Llama-Factory without any further adjustments. It's ready to go. To make this architecture even more powerful, we added a search utility feature. Developers can actively stream the dataset and search for specific keywords or target specific task sources, like NL2 Bash, for example, yielding only highly relevant traces. It makes a vast, intimidating 1.7 million row dataset easily searchable and highly modular. This empowers developers to instantly pull exact slices of data for their highly domain-specific projects. So we've seen how to take a massive, unstructured dataset, stream it without crashing our memory, normalize the chaos, extract the core commands, visualize the behavioral trends, and filter it completely down into high-quality training fuel. The pipeline is built, and the raw data is just waiting. So the only question left is, how will you tap into AgentTrove to refine the fuel for your next domain-specific AI? Thanks so much for joining me on this explainer, and happy building.